Let's continue with Chapter 2, Section 2.4, Chemical Formulas. There are lots of different ways to represent compounds, atoms, elements, and molecules. One is the molecular formula. You already know this. H2O is a molecular formula. It is the formula for the compound. 2 hydrogens, 1 oxygen. So here you're seeing the importance of a chemical formula. H is just 1 H atom. 2H would be 2 H atoms. But H2 with the subscript is 1 H2 molecule. And 2H2 would be 2 hydrogen molecules. So make sure you appreciate the difference between putting the number in front of the chemical symbol and as a subscript, because they convey 2 different pieces of information. Some elements on the periodic table exist as molecules in their natural state. For example, hydrogen. There aren't H atoms in nature. There is only H2. There aren't oxygen atoms in nature. There is only O2 as a molecule. What you're seeing here is a very convenient and useful mnemonic device for remembering those elements that exist as molecules in nature. And it goes like Brinkelhoff, bromine, Br, iodine, N, nitrogen, Cl, chlorine, H, hydrogen, O, oxygen, F, fluorine, Brinkelhoff. All of these are the diatomic molecules that exist in nature. And you'll see when you do problems, a substance reacts with oxygen. You wouldn't say plus O, you would say plus O2, because it's implied that oxygen is a molecule, not an atom. So make sure you appreciate this when you're doing homework problems. There's the molecular formula and the empirical formula. The empirical formula is the simplest whole number ratio of the atoms in a compound. So take a look at a couple of examples here. Benzene has a molecular formula C6H6, but the lowest divisor for C6H6 is if you divide both of these by 6, 6 over 6 is 1, 6 over 6 is 1, the empirical formula is CH. So you divide the subscripts to get the lowest possible divisor for each one. Here's acetic acid, C2H4O2. Well, you can see 2, 4, and 2 are all divisible by 2. So divide each of these by 2, and you get CH2O as the empirical formula. This is important because later in the course, we'll find a way to go from the empirical formula to the molecular formula. So make sure you appreciate the difference. Let's talk about the periodic table. This was accomplished, arranged, organized by Mendeleev in Russia and Meyer in Germany. And what Mendeleev did was organize elements according to their chemical properties. Are they shiny? How do they react with oxygen? Are they good conductors of electricity? and so forth. And when he did that, he came up with a periodic table. I know this is difficult to read, but basically why he is remembered is based on his arrangement of the periodic table. He predicted the existence of elements that had not been discovered yet. Based on his arrangement, he knew that there should be an element germanium beneath silicon, and germanium was discovered in Germany shortly after he predicted it to exist. So he is remembered as the father of the periodic table. Keeping it short and simple here. So we have the periodic law, and we know that the elements are not arranged according to their property. They are arranged according to their atomic number, Z, the number of protons. That is the modern periodic table. Why is it called the periodic table? Because properties repeat themselves. They are periodic. That is why. A modern periodic table has groups that are vertical columns numbered 1 through 18, and periods which are horizontal. And so let's take a look at some of these groups and periods. So here you're seeing the group going across 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 18. And there are 7 periods, or 7 horizontal rows. You can see right here, I'll talk about this later, that on the far left, you're seeing the beige. All those are metals, while on the far right are non-metals, and in between are the metalloids, which have properties of both metals and non-metals. Silicon is perhaps the most important example of a metalloid, used as a computer chip and many other things. Metals are shiny, malleable, good conductors of heat and electricity. Non-metals are dull and poor conductors of heat and electricity. And metalloids have the properties of both. So we can divide the periodic table into the main group elements, and this is very important to understand the main group. Why? Because the laws of chemistry, all the rules that you're going to learn, are very consistent for main group elements, but are not consistent for transition metals. So the main group elements are groups 1 and 2 and 13 through 18. 1 and 2, we skip over 3 through 12. These are called the transition metals. And 13 through 18 are also main group elements with very consistent laws and rules that predict their behavior. So here's a nice way to look at the periodic table. You have the main group elements. Why is, oh, I see. Here are the transition metals, the main group elements, groups 1, 2, 13, 14, 15, 16, 17, 18. And you're seeing some names for some of these. And all I would like you to know are 4 of these. You should know that the group 1s are called the alkali metals. Group 2 are called the alkaline earth metals because they're common in the Earth's crust. And then you can skip over the pnictogens and the chalcogens. And I want you to know the halogens, fluorine, chlorine, bromine, iodine, and astatine, and the noble gases. Those are the common names that you should definitely know. In this class, we don't really talk too much about the lanthanides and the actinides, but just so you know, if you look on the periodic table, it goes barium 56, and then it skips to 57 through 71. Those are the lanthanides. And then the actinides are in group, period 7, 89 to 103. So those are represented as two separate periods. Even though they're part of period 6 and 7, they're long, and so to make a convenient representation of the periodic table, you see that they're given their own separate rows here on the bottom. Okay. 2.6, molecular versus ionic compounds. There are basically two ways that elements bond to each other. We've said earlier that all of chemistry, apart from nuclear chemistry, is shuffling around the electrons. That's true. There are two basic ways that that can be done. Either one element gives its electron to the other, and the other one accepts it, or the electron is shared between the two atoms. So it's the difference between a transfer of electrons and a sharing of electrons. And we'll see that that has to do with the type of compound that is being formed. In short, ionic compounds transfer electrons and molecular compounds share them. So here we're seeing an atom of sodium. It has 11 protons and 11 electrons. When it ionizes, we talked about this in part 1, it can lose an electron. So here you're seeing it has 10 electrons in slide B, and then it becomes Na+. So the plus means it's missing an electron. That's what the plus means. The electron has a minus charge. So if it has 11 protons and only 10 electrons, it has one more proton than electrons. That is why it is represented as a +1 charge. The 1 is implied. Okay, how to predict ion charge? Well, I'm just going to cut to the chase. Here it is. You should have this very handy when doing homeworks and on exams. You're seeing that groups 1 and 2, some of the transition elements, and 14, 15, 16, and 17, aluminum in group 13, all have what's called invariable charges, meaning that when these elements form ions, they form ions in these states, in these forms. In other words, every element in group 1 is a +1 charge. All of these elements have one more proton than an electron. In group 2, notice that group 1, the group number is the charge. So that is true for groups 1 and 2. You're seeing beryllium, magnesium, calcium, strontium, barium, and radon all have a +2 charge, meaning they have 2 more protons than electrons, or they want to lose 2 electrons, basically saying the same thing. Take a look at chromium as a transition metal. Notice that it can have 2 charges. It can either be a +3 or a +6. Iron can either be a +2 or a +3. Copper can either be a +1 or a +2. Gold can either be a +1 or a 3, and mercury is very wonky. It's Hg2, two mercury atoms connected together to make a +2, or you can just have one mercury atom as a +2. Again, a little bit wonky. Aluminum is always +3. Carbon is 9 times out of 10 -4. The group 15s, nitrogen, phosphorus, and astatine are -3. Group 16s, -2. The halogens, -1. And the noble gases would be 0. They are called noble gases because they neither gain nor lose electrons. So this is a table showing those elements with invariant charges that do not change. Although some of the elements, particularly the transition ones, do have different charges on them. So as you'll see, this is very important when predicting a lot of different things in chemistry. So we talked about ions, cations versus anions. Let's talk about another type, the polyatomics. Poly meaning many atoms. So we have the polyatomics, and we'll see the oxyanions. Oxy meaning containing oxygen, anion meaning they are negatively charged, and we'll see that they can have one or more oxygen atoms associated with them. Here is a nice, very long list, which you should also have handy with you when doing homeworks and taking exams. I will try to put these as separate tables for you on Blackboard. Ammonium, NH4+, hydronium, H3O+, peroxide, O2-, hydroxide, OH-. Don't forget when using these formulas to include the charge. It's not just OH, it's OH-. It's a polyatomic oxyanion. Azide, N3-. Carbonate, CO3-. Bicarbonate, I know that's confusing, bicarbonate, it's HCO3-1. Nitrate, nitrite, sulfate, and so forth. The list continues. And so this is a very handy list for the list of polyatomic ions that you will need to understand and use. Okay. We're going to talk about nomenclature. Nomenclature is very important in chemistry because there are literally millions of compounds to name. So we need to have a systematic way of naming them. So if you have a nonmetal that forms two oxyanions, so let me give you an example here of nitrate versus nitrite. Note the ending, ATE versus ITE. Nitrate is the one with more oxygen atoms. It has 3 oxygen atoms. Ite, the ending ite, always has 1 less oxygen than 8. So to go from the 8 to the ite, you just subtract an oxygen. Notice that the charge does not change. Both of these are -1. Look at sulfate and sulfite. Sulfate, SO4-, compared to sulfite, SO3-, and you're seeing, again, the ite ending tells us that it has 1 less oxygen than the 8. So you could do the same thing with phosphate and phosphite, not listed on here. And so I think you understand the pattern. Here is chlorite versus chlorate, another example. Okay, so that's ate versus ite. When a nonmetal forms more than two, prefixes are used in addition to ate and ite, and we have two more, per and hypo. So per is above ate. So if it has more oxygens than ate, it becomes per. And if it has less oxygens than ite, it's hypo. So there's only a couple of examples of that. Here's the classic one, the four chlorates. Here's chlorate. Start with chlorate, ClO3 minus. One more than ate is perchlorate, ClO4 minus. Notice again, they all have the same charge. Here's chlorite, one less than ate, and there is hypochlorite, ClO minus, which of course is the ingredient in bleach, sodium hypochlorite. So that is how you name compounds that have more than two oxyanions connected with them. Ate, ite, per, and hypo. All right, we'll get back to nomenclature in a little bit. As I said, when electrons are transferred, it becomes an ionic bond. So the classic example of an ionic compound is sodium chloride. The sodium gives up its electron to become Na+. As we saw, it wants to become Na+ as a cation. Look at chlorine. It becomes an anion. It gains an electron. So sodium wants to lose it. Chlorine wants to gain it. They form an ionic bond. Ionic bonds are formed between metals and nonmetals. Covalent bonds or molecular bonds are formed between two nonmetals. So for example, CO2 is carbon dioxide, would be a molecular compound. NO, nitrogen monoxide, would be a molecular compound, two nonmetals. So that is the pattern there. Metals lose electrons to form cations. Nonmetals gain electrons to form anions. You can see that in the table I just showed you. When a metal and nonmetal react, the electrons are transferred. That is an ionic compound. Here you see the example of sodium and chlorine, and another example of calcium and chloride. Notice that calcium chloride is CaCl2, whereas sodium chloride is NaCl. So I'm going to teach you how to correctly write the chemical formulas between two atoms in a little bit. Ionic compounds have high melting and boiling points. They're non-conductive to electricity as solids. Sodium, table salt, does not conduct electricity and has a high melting point. In their molten form, they do conduct. So here just an example of a light bulb going off as you convert halite. Here's halite, the light bulb isn't going on, non-conductive. You heat it to 800 degrees Celsius, it becomes molten, the light bulb goes on, meaning that molten sodium chloride conducts electricity very well, actually. Okay, formulas of ionic compounds. I'm going to show you how to do this. and it's very important for the homework and the exams and all that. So I'm going to switch to DocuCam here. Okay, here's how we do this. We take the two atoms. Let's see, calcium why do none of these work? Calcium and chlorine. These are the two elements that we want to combine. And the question is, what is the formula, the molecular formula of how these two elements combine? The first thing you do is look at the charges of the elements as ions. That's why it's important to be able to use the table of the charges so that you can easily know the charges on these elements as ions. Calcium is in group 2, it's a 2+. Chlorine is in group 17, it's a -1. All the halogens are -1, all the group 2s are +2. So that's the first step. These two elements have to combine so that the compound is neutral. The compound has to be neutral, meaning all the charges sum to 0. So you're seeing +2 plus a -1 is +1. That's not 0. So you cannot just write CaCl because +2 plus a -1 +2 plus a -1 is the same thing as +2 minus 1, which is +1. That's not 0. So this is wrong. The trick to do this is that the charge on the first element becomes the subscript on the second element. And the charge on the second element becomes the subscript of the first element. And now you can quickly write down CaCl2. You can check your work. -1 plus -1 is -2. -2 plus 2 is 0. The charges sum to 0. You can always check your work. This is correct. Let's do another one. How about a polyatomic? How about a PO4 phosphate? That's one of the ones in the table. It's a triple minus plus sodium. How do these, it's not really plus, it's how do they combine? So we play the same game. The subscript, the charge on the first one becomes the subscript on the other one. I call it the old switcheroo. And so notice you always have to write the cation first. Cations get written before anions by convention. So this becomes Na3. Now I've got one phosphate, PO4, like that. Sodium phosphate. All right, let's do another one. FeNO4. and O. Fe can have multiple charges, as we saw from that table. Let's just say it's Fe3 plus. It will have to state for iron which one it is, either the 2 or the 3. If it doesn't say what it is, you can't really do iron. Oxygen is in group 17. It's always a double minus. So we have a 3. That becomes the subscript. The 2 becomes the subscript for the iron. And we have Fe2O3, like that. Check it. Plus 3 times 2 is plus 6. Minus 2 times 3 is minus 6. Minus 6 plus 6 equals 0. All right. Let me try to think of one where you need something else to learn. How about Fe3 plus and OH minus? Here's a good example. Fe3 plus and hydroxide ion, that's on the list. So we do the same thing. Fe, and now the 3 is, we got 3 hydroxides. So we need parentheses, OH3 like that. Notice you don't write the charges. There's no charges in the neutral compound. You don't have to write that. Note the use of parentheses when you have multiple polyatomic oxyanions. So that's another thing to keep in mind. So these are several examples of how to write the correct chemical formula for 2 elements that will combine to make ionic compounds. So hopefully that will get you through the homework problems with some fun and ease. Oh, they did a nice example here done out of calcium phosphate, Ca2 plus and PO4 triple minus. Note again the use of parentheses around the polyatomic oxyanion. You need 3 calciums because plus 2 times 3 is plus 6. Plus minus 3 times 2 is minus 6. Minus 6 plus 6 is 0. This is a neutral compound. It is correct. Molecular compounds arise when electrons are shared, and molecular compounds exist as discrete neutral molecules formed by a combination of nonmetals, as I showed you earlier, are often gases with low boiling points and low melting points. Sort of the opposite of ionic compounds. Okay, let's talk about nomenclature. I already gave you a little bit of nomenclature with the 8 and the ite. Let's go in a little more detail. Compounds are identified by their formula and name. We are going to learn how to name several different types of compounds. One is ionic and molecular binary compounds. Binary is just a fancy name for 2. 2 different elements combining together. That's a binary compound. And we'll talk about polyatomic ions. How do we name those? And sorry, the third type will be acids. How do you name acids? Okay, when naming ionic compounds, you name the cation first, followed by the name of the anion. Think of naming for this section, think of sodium chloride, NaCl. The cation comes first, followed by the name of the anion. Notice that chlorine becomes chloride, sodium chloride. Notice the IDE ending on the binary ionic compound. So you change the ene to the I. For a polyatomic, this is why you need to know the names of the polyatomics, because that is the name that is used when naming the compound, if it connects to one other element. Here are some examples. Only monoatomic ones, no polyatomics here, but good practice: sodium chloride, potassium bromide. Notice you don't change anything on the cation. It's just the name of the element, but the anion has the ending change to IDE. All of these have IDE endings. Cesium fluoride, lithium chloride, aluminum carbide. How did they come up with aluminum carbide? Al4C3. That's a tricky one. Not sure I would give you one that challenging. Carbide. See, carbon is a 4 minus, and aluminum is, oh, there it is. So the 3 goes to the carbon, and the old switcheroo works again. I probably wouldn't give you one that challenging. The azide. There are some ones that are just tricky. The carbide these are tricky ones. Probably we don't need to get into that level. But I would put magnesium nitride on there because that one is consistent with nitride. Let's look, Mg3N2. Mg3N2. Mg is 2 plus, N is 3, so Mg3N2, you can use the old switcheroo actually in all of these cases. So this one is nitride, that one is carbide, P3 minus is phosphide. So those are the ide endings for some of the anions. Here are some polyatomics now. This is why it's important when naming compounds to have that polyatomic ions list handy. We have acetate. That is C2H3O2. All C2H3O2 is the acetate. If you go back to the polyatomic list, it's right on there. And potassium acetate, the potassium comes first. Ammonium chloride, ammonium NH4 plus, chloride Cl minus. Sodium bicarbonate, bicarbonate is HCO3 minus. So you're seeing the pattern here that you just put the cation first, followed by the actual name of the polyatomic ion. Aluminum carbonate. Notice here you have parentheses, carbonate is CO3. That's on the list. And you've got 3 of them. So you need a parentheses and then a subscript 3. So make sure you can count up all the ions here. Well, excuse me, all of the elements. So aluminum carbonate has 2 aluminums. It has 3 carbons. because the 3 means 3 of the whole thing, 3 units of carbonate. So there are 3 carbon atoms, and there are 9 oxygen atoms in aluminum carbonate. And then magnesium phosphate. Okay. What we've done so far is make compounds and name them if the charge doesn't change. But as we saw on the list, elements like iron and copper and gold and other ones have multiple charges. Iron can either be a +2 or a +3. Copper can either be a +1 or a +2. And so to represent that, we use Roman numerals. So when you say iron 3 chloride, that means that iron is in the +3 state, and the formula would be FeCl3 iron chloride. Mercury 1 oxide is Hg2, that's mercury 1. That's why it's confusing. It's mercury 1, but there's 2 of them with a charge of +1, and then oxygen I. Mercury 2 oxide would just be HgO. Copper 2 phosphate. Phosphate we know is -3. -3 times 2 is -6. So copper is in the +2 state here, indicated by the Roman numerals. Okay. For molecular compounds, it is a completely different set of rules. Make sure you use the correct set of rules for molecular compounds versus ionic compounds. We just did the ionic compounds. Let's do the molecular. Okay. Molecular compounds have prefixes. Mono, di, tri, tetra, penta, hexa, hepta, oxa, nona, and deca. You can omit the 1 if there's only one of them, like take carbon dioxide. That is a molecular compound composed of 2 nonmetals. It's not monocarbon dioxide. The 1 is omitted because it's implied. If there's no number there, it's a 1. So in molecular compound, we use prefixes. Here's some examples. Sulfur dioxide. So note the prefix di, because there's 2 oxygens. So to name SO2, you wouldn't say sulfur oxide. That would be naming it as an ionic compound. You need to use the molecular rules, which are the prefixes. So it's sulfur dioxide, BCl3, boron trichloride, sulfur trioxide. Look at sulfur hexafluoride, hexa meaning 6. Nitrogen dioxide, di meaning 2. Phosphorus pentafluoride, penta meaning 5. And look at N2O4. Now you do need a prefix for the nitrogen because there's 2 of them. So this is dinitrogen tetroxide. P4O10 would be tetraphosphorus decaoxide, and so on and so forth. So I think fairly straightforward. In molecular compounds, you use the prefixes to tell how many there are. And again, with the IDE ending, and the first element stays the same. Sulfur, boron, nitrogen, and so forth. Okay. So I'm going to skip over naming acids. We will not include that in this class. You can learn that in a later class. So the only thing for naming is naming ionic compounds with the polyatomics, and naming variable charges, and naming molecular compounds. And that will be it. And you'll see on the homework on chapter 2, there are some problems asking you to look at these things. Okay, that is it for chapter 2.